Okay, physicists, if you missed the lesson on fusion, then this is an opportunity to go over those ideas, or if you just want to have a bit of a revision and catch up. Okay, so nuclear fusion, before we get onto that, just a quick reminder of what we'd learned about prior to that, which was nuclear fission. So nuclear fission was taking a large nuclei, and I'm not going to draw the whole thing out, lots of little circles, but hopefully you get the idea that this uranium is made up of a total of 235 protons and neutrons. And what we learned with fission is that could break down into a couple of smaller, what we call daughter nuclei, and some neutrons. I should probably have done those blue. There we go, to represent that, and that can cause a chain reaction. So that's what we learned about prior to this. So the key thing here is that when uranium-235 absorbs a neutron and breaks down, it releases energy. So nuclear fission releases energy. Okay, so we're going to look at nuclear fusion today. Rather than a large nucleus forming to or breaking down into a smaller one, what we get with nuclear fusion is smaller nuclei joining together to form a larger nucleus. So if we just give ourselves a little reminder about isotopes, any nucleus with one proton is going to be hydrogen. Most hydrogen, hydrogen 1, it doesn't have any neutrons, but what we've got here are two isotopes of hydrogen that can be formed under certain conditions. And so we've got hydrogen 2 and hydrogen 3. And what can happen when these two, again under very specific conditions, interact with each other is they can join together. We need to learn about what those conditions might be for them to join together. And when they join together, they're going to form a different element. And hopefully we've done this one a lot because it's an alpha particle we get when this, so it's a helium nucleus. So we're also still going to get that neutron isn't going to disappear, so we've also got a neutron on its own as well, which may go off and either decay into a proton. For the moment, what we're interested in is this idea that we have formed a larger nucleus from smaller nucleus, or smaller nuclei, and of course the key thing here is we also get energy. Now you might be asking, how comes we get energy from fission and fusion? That is for another day or another video. We went through that in class, but for the moment I want to stick to the basics. But both of them give out energy. Before we look at the specific specification points, I just want you to think about why fusion is a difficult process. So I've just got a couple of questions. When I put them up, pause, have a think of an answer for yourself, and then I'll go through it with you. So what charge do nuclei have? What charge do nuclei have? Don't get caught out by the idea that an atom's got a neutral charge, because of course the nuclei only has the protons and the neutrons. So if a nucleus always has protons and neutrons are neutral, obviously the overall charge of a nucleus is going to be positive. What do you know about the electric charge, or about electric charge and forces? Hopefully you know something about what like charges will do and what opposite charges will do. And hopefully you know that the relationship is that like charges will repel each other and opposite charges will attract each other. And so if that is true, hopefully that leads you to why it is difficult to get two nuclei close together. If we, just for argument's sake, keep it simple and just imagine we've got two hydrogen 1 nuclei, so just two protons. The reason that it's going to be very difficult to get these close together is that even if their motion were to be together, they're going to experience electrostatic repulsion, and so as they approach each other, they're going to divert off on a different trajectory. So basically fusion doesn't just happen under typical conditions that we get on Earth. This is an example of a fusion reactor. This is a tokamak reactor. So we do have working fusion reactors. As you can see, though, this is very small. We've got a person here in this reactor, and so what we've not yet achieved is to be able to build a nuclear fusion power plant on a large scale that would deliver large levels of electricity. And at this stage, we don't need to go into all the complexities of why, but what we do need to think about is just why fusion is difficult, and that takes us on to our first specification point. Okay, so we can see how big a topic this is. We're on point 43 at this stage, so 6 for radioactivity, 0.43. A reminder that the P is telling us that this is triple only content, so if you're watching this, this is triple only content. This is not in combined science. Okay, describe nuclear fusion as the creation of larger nuclei, which we've talked about already, resulting in the loss of mass of smaller nuclei, which we haven't talked about, so we'll go into that in a second, accompanied by the release of energy, which we have talked about, and that this is the energy source for stars. So I've put our sun in here as an example of a star that's carrying out fusion reactions. So we've got this idea that larger nuclei are forming from smaller nuclei. What we didn't discuss was the loss of mass. And again, we bring up this equation. It's not directly stated on the GCSE specification, but it might just help us to think about what's happening. So c is the speed of light. I'm not going to go into why the speed of light happens to be on this equation. I just want you to understand that it's a very big number. So 300 million meters per second. Of course, we're going to square that number, so it's going to get even bigger. So that is a very big number. And what it tells us is that when we convert between mass and energy, because we can convert between mass and energy, the amount of energy that we get out of a amount of mass is multiplied by the speed of light squared. So basically what we're saying is a small amount of energy will give us, a small amount of mass will give us a very large amount of energy. And when we're carrying out a fusion reaction, our product, let's say we've got our helium and our neutron. So we've got this from our starting point of, remember we had hydrogen 2 and hydrogen 3. So this is what we started with, and this is what we're ending with, helium 4 and a neutron. So what you might think is, well, there's no mass lost. I've got 2 plus 3 over here, so I've got a mass, 5 atomic mass over here, and I've got 4 plus 1 over here, so I've got 5 over here. So in terms of to the nearest whole relative atomic mass, we're not going to see a change in an individual fusion reaction. But if we looked at the the decimal place on this, or if we looked at the precise mass, what we'd find is that this side would have less mass. And that relates to the loss of mass from smaller nuclei. So we've got less mass here. Why is that? Again, we're not going to go into that now, other than just understanding that because we've got less mass, where has that mass gone? Well, it got converted into energy, and that's how we got energy out of a fusion reaction. Mentioned before, how comes we get energy out of a fission reaction as well? The relationship is not linear to whether we're making a larger nuclei or a smaller nuclei. So as I say, you don't need to know that for GCSE, but that could be another question for another day. So fusion as the creation of larger nuclei, resulting in the loss of mass from smaller nuclei, and recognize that energy is a fusion source for stars. So basically, this is what stars are doing. They are converting smaller nuclei into larger nuclei. So all the stars in the sky, they are all fusion reactors. It's part of what gives us the definition for a star. A star has to be big enough that it's carrying out fusion reactions. And so that is the energy source for the stars. It also, when we discovered this, allowed the universe to be a lot older than we'd perhaps previously had evidence for, because if a star was combusting material in the traditional way of chemical combustion, they wouldn't be able to last the billions of years that they do. So it was an understanding of nuclear fusion that made us realize that stars could exist for billions of years. Okay, 6.44p, explain the difference between nuclear fusion and fission. Hopefully, if I've explained things well enough, you'll understand this by now. I'm going to not spend too long. Fission, we're taking a large nuclei, we're breaking it up into smaller nuclei, and usually some neutrons. And fusion, we're taking small nuclei, adding them together into bigger nuclei. They both give out energy, so obviously that's something that's the same, and the spec point is what's the difference between them, but worth noting that the thing that's the same is that they both release energy, these processes, but the difference is fission is large nuclei breaking down into smaller nuclei, and fusion is small nuclei joining together to form bigger nuclei. Okay, 6.45, explain why nuclear fusion does not happen at low temperatures and pressures due to electrostatic repulsion of protons. Okay, so this one is, I suppose, the most complex point probably. It's related to why fusion is difficult. So let's imagine that we have two protons and they're moving towards each other. I showed this in one of the earlier slides, but the idea is because like charges, in this case nuclei, are always going to be positive, because like charges repel, as these two things approach each other, they're going to feel a force of repulsion, and so that's going to either force them to divert off course or change direction so that they don't touch each other. Okay, electrostatic repulsion of protons means it's going to be very hard to force them together. You've probably tried to push the ends of a magnet together before and you can feel that force. Well, now imagine that the closer you get, the stronger the force becomes and the harder it is to get them together. But what you also know from chemistry and some of the work in physics is that as we increase the temperature of something, the particles in that substance start to move faster. And if we've got higher pressures, then again we are forcing more particles into a smaller area and we're increasing their velocity. So as they approach each other, let's say we now have another pair of protons, but they happen to be moving much more quickly towards each other. Their motion, their speed, let's say, or represent, or we could do it in a number of ways. They are now moving much more quickly towards each other. Now, they're going to get much closer because they're going so fast that they're almost going to potentially come into contact before they divert. Now, if we create such huge temperatures and pressures like those that we get, like those we get in stars, then what we're going to find is that the protons do get close enough and that they are able to fuse. I've just done it simply here with protons rather than the isotopes of neutrons, just for simplicity's sake. But they become so close together they fuse, and there's a force that you don't need to know the name of for GCSE, but I might as well tell you, very boringly named, it is the strong nuclear force. And it literally is what it says. It's a nuclear force, so it acts in the nucleus and it's very, very strong. Now, the reason it doesn't bind protons or hydrogen together all the time is that it works over a very, very short distance. So normally, under normal conditions that we get on Earth, hydrogen atoms might approach each other, but they would repulse each other and they wouldn't get close enough for the strong nuclear force to take effect. In the very, very high temperatures and pressures that we get in stars, it's able to force those hydrogens close enough together that the strong nuclear force takes over and it binds those things together. So that is why a nucleus stays together. It's because of the strong nuclear force, even though there is an electrostatic repulsion. The strong nuclear force is stronger, but it doesn't act over a very long range. Okay, and last specification point for fusion is 6.46. Relate the conditions for fusion to the difficulty of making practical and economic form of power station. So going back to the previous point, okay, the conditions for fusion, we've said, have to be very high temperatures and pressures to overcome electrostatic repulsion. So it is very difficult to create conditions that are similar to that of a star. I showed you this this tokamak earlier. This tokamak is the name for these types of fusion reactors, but as you can see, it's small. We are able to carry out fusion reactions, but we haven't yet successfully done it on a large enough scale. So that's what it's talking about in terms of practical and economic form of power station. We cannot generate the levels of energy to power towns and cities. We have not worked out how to solve that problem just yet. And the reasons for that are because the conditions for fusion are very hard to recreate. We can do it on a small scale and we can get a few reactions to take place, but we cannot do it on a scale that produces electricity. But that's hopefully, you know, why we teach this. We want you to be excited and inspired and try and solve these problems, because it really would like completely change the world if we were able to create relatively extremely clean compared to some of the methods we use now, and almost endless supply of energy. The world would be changed. So yeah, that final point is just about relating to the previous point on those high temperatures and pressures are difficult to create, and therefore we have not yet made a practical and economic power station using fusion. I hope that was useful. Any questions, stick in the comments. Thanks.